This is math and beats. You just had some beats. Now it's time for some math. Today we're making a video on how to graph functions of one variable. So let's talk about this. First, let's define what a function of one variable actually is. A function of one variable is a function that can be written in the form y equals f of x. Notice there's only one input value. That's x. There's only one output. That's y. The result of applying the rule f to x. Hence, a function of one variable is determined by how many inputs to the function there is. Things like y is f of x is x squared, one variable. Y equals f of x is x. Y equals f of x is square root x. Notice all of them have the single variable x, one variable. You can make other things up. W is g of t is t minus 3, one input t, single variable or one variable function. Or even alpha is h of k is k cubed minus 2k. All of these are examples of a one variable function or a single variable function. One input, one output. That's what we're going to focus on graphing right now. Functions like this. So let's refresh what the graph of a function actually is. As we see right here, the graph of a function of one variable is the set of all the ordered pairs x comma y's plotted in the Cartesian plane, satisfying the function y equals f of x, where the x belongs to the domain of the function and the output y is belonging to the range of the function. So if we took all such ordered pairs that satisfy that equation, y equals f of x, all, even if there's infinitely many, and plotted them all in the Cartesian plane, we would get what's called the graph of the function. So we're going to do a couple now. Here is an example. We have given to us the function y equals f of x is x squared. So the rule here, take the input x and square it to get the output y. Now, we should note that the domain of this function, domain of f here, is all real numbers. So it doesn't matter which number we plug in. This function is going to be defined, and we can't graph all of the ordered pairs, but we'll graph some. So what we're going to do is make a little table, x, comma, f of x's, and the resulting ordered pair. So we'll do several of these, plot some points on the Cartesian plane to the right, and then we'll see a pattern, hopefully. And we'll say, look, we see the pattern, we can plot all of them, and then we'll connect the dots and draw a beautiful graph. So let's just start with maybe, since we see in this Cartesian plane here, our x values range from -4 to 4, and our output values from -1 to 9. So we have that little rectangular region to work with. We got to pick ordered pairs accordingly. How about when x is 0? If x is 0, then we get 0 squared is 0. So the ordered pair 0, 0 is on this graph. Down here, draw a little dot, 0, 0, boom. Pick some more. How about if x is 1? 1 squared is 1, so we get the ordered pair 1, 1. 1, 1, boom, plot the point. How about if x is -1? Well, then -1 quantity squared is also 1. So we get the ordered pair, -1, 1. Plot it right there. So we're starting to see something happen. Let's pick a few more positives and negatives for the inputs. How about if x is 2? Then 2 squared is 4, and we get the ordered pair, input 2, output 4. Let's plot that, 2, 4. About right there. How about when x is -2? -2 squared is also positive 4. So we get the ordered pair, input -2, output 4. About right there on the graph. Couple more, maybe we can start seeing the pattern. If x is +3, then 3 squared is 9, and we get the ordered pair 3, 9. Plot the ordered pair 3, 9 on the graph. And then finally, input -3, -3 quantity squared is 9 as well. We get the ordered pair -3, 9. -3, 9. So we start to see this shape. And you could pick more inputs, obviously, like say if 1.5 was your input or -2.3, right? Then we can make a guess kind of where these things would be based on the behavior of this graph. And that is, as x gets bigger, this graph is going to get bigger. I square a number, it's going to get bigger in the long run. And likewise, because negative and positive numbers, both when squared, results in a positive number, as the x gets bigger in magnitude towards negative infinity, then we're going to behave the same way, and that is we're going to grow in output value. And now we're going to attempt to kind of just draw in what this would look like. You can see that as the x values get larger in magnitude, this thing grows even faster and faster. We'll do our best here to make a nice smooth curve. So something, put the big dot right there. And yeah, you know what? I don't like that. Let's draw it one more time. Try to connect these. Okay, we're getting down here. Hit that thing. Come back up. And keep going. And we get a shape that looks something like that. Obviously, if I had better hand coordination, I probably would draw a much more beautiful curve. But that is the graph of the function. This is the graph of y equals x squared. It's actually a graph of what's called a parabola. It's a certain shape. Quadratic functions have the shape of a parabola. So we could make it more accurate by picking more and more and more and more and more inputs and finding the corresponding outputs and plotting all kinds of the ordered pairs. But overall, we can be pretty confident that's what the graph looks like, more or less. All right, one more example. How about now we look at the graph of a function y equals f of x is the square root of x. Again, we'll make a little table to help us along. Make a table with x's, with f of x's, and the corresponding ordered pairs. Now, before we start plugging in x values, inputs, we should note what the domain of this function is. The square root of x, remember, tells us that the x cannot be negative. So we can only plug in 0 or positive values. For this reason, the domain of this function is the interval bracket at 0, parenthesis at infinity. So all the non-negative real numbers. Alright, so that means I'm not even going to bother putting in negative values of x. And now I'll just start at the smallest value of x, maybe a 0. So if x is 0, then square root of 0 is 0. So we get the order pair 0, 0. So this function as well got the order pair at the origin there as part of its graph. Now we'll pick some nice numbers going forward because we got perfect squares as inputs would result in nice outputs. Like for instance, if x is 1, then the square root of 1 is 1. And we get the order pair 1, comma 1. So 1, comma 1. Pretty nice, pretty nice. How about some more? How about if x is 4? Then the square root of 4 is 2. And we get the order pair 4, comma 2. Right about there. So you say, I'm starting to see a little bit of a pattern here. It's definitely not a line. Kind of goes up and then takes a while to get a little bit bigger there. And so if we picked one of these other numbers that's not a perfect square between 1 and 4, like for instance, if x is 2, then the square root of 2, well, 2 is not a perfect square, so this is a numerical approximation. You could plug it into the calculator and figure out approximately what it is, but I just happen to know off the top of my head it's approximately 1.4. So we get the ordered pair, we should probably say approximately 2 comma 1.4. 2 comma 1.4, about right there, just to give us another point, at least approximately, to see more and more of what this pattern may be. Now, if you think about it, the bigger values of the inputs that we plug in, then square root's going to get bigger as well. Square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, and so on and so on and so on. So this function continues to get bigger in the output direction as our inputs get larger, but it's kind of a slow growing function, if you will. So you connect the dots here, you get a graph that looks something like so. This is the graph of the function, y equals square root x. And there you go. We plotted a couple functions. So this is how you plot all functions really in single variable until you learn them really well and you just know what the graphs look like and how they behave. Nice little method. Make a table of ordered pairs, plot them. If you need more ordered pairs, then do so, and you get the pattern of the graph and you connect them with a curve. We did x squared and square root x. Got these graphs right here. These end up both being elementary functions, which will be talked about in a different video. And so in general, our interest in math for the time being is graphing functions of one variable, of a single variable, in the form y equals f of x, or any function that could be written as so. The graph, of course, is the collection of all the ordered pairs x comma y's, which results in applying the function rule f to allowable input values x and getting some output. You plot them all, you get the graph, and we saw a couple graphs. So that's a little intro. That's how you graph. We're going to look at so many functions graphs. It's going to be great. Oh yeah. So math and beats is it. It's time for beats. If you like the math or the beats, make sure you press thumbs up, buddy. Thumbs up. Alright, peace, y'all. Later.